Now we're going to begin our discussion on Chapter 3, which is fluid statics. And recall that a fluid is any material that deforms continuously under an applied shear. So now for fluid statics, there's no flow. So that begs the question, if there is a shear stress, then there's motion of the fluid. But what if there's no net motion of the fluid? Okay, and what that means is that if there's no net motion of the fluid, that means that the velocity vector is exactly zero and constant. And of course, if the velocity vector is zero, then that means there is no shear stress, because recall that the shear stress of a fluid, oops, got rid of that, is tau equals mu, which is the viscosity, times a velocity gradient. Now, in reality, the expression is a bit more complicated than that, so that's just an approximation. But so it's related to the velocity gradient, and if the velocity field is zero and constant, that means this is zero, which means that there's no shear stress. Thus, if the fluid is static and the equilibrium and the state of stress is typically this, well, we know that because it's in static equilibrium, all the shear stresses are zero, so we can cross out these terms over here. Now, how about the normal stresses over here? What do we do about those? Okay, and we can show that if there's no net motion, that all of the normal stresses turn into negative p. Okay, and so this stress tensor this stress looks like that. And in reality, here what we are studying is hydrostatics. And hydrostatics is the study of fluids in static equilibrium. It's just like how you took an entire course in statics before you did dynamics. Okay, and so if you want to look at it this way, you sort of pretend we have a little tank. Right here, it's filled with some water. And remember that this little triangle with the three lines underneath it, that means that you're at atmospheric pressure, okay? So this means that P equals PATM equals atmospheric pressure. Okay, so now let's look at a little stress element here. And so we just draw our sort of stress square, and we're just noting that that the velocity is zero because we're assuming it's in static equilibrium, and the velocity gradient is also zero. Okay, and so now we're just going to apply an equilibrium stress condition to this, noting that all the shear stresses are zero. Okay, and so that means this stress element becomes this. Well, I have defined that if there's no motion, then all of these just turn into minus pressure, like you see here. Oops, and I got to do one more. Okay, and so that turns into this stress tensor here, and then eventually this is in static equilibrium, neglecting the weight of the fluid in this little square. Okay, so we're just left with pressure pushing on the surface of each thing. And where this sort of where this comes from, you can the normal stress is actually defined to be minus pressure plus some viscous contribution. Okay, and if there's no net motion, the viscous contribution is zero, and so you can cancel that out because there's no net motion. Thus, in static equilibrium, the normal stress is equal to minus p. Okay, and so now we're going to address the question: is what we are interested in is, say we have a tank, it's filled with water. We have a little triangle here. and we're at some depth d. What is the pressure at depth d? Well, how do we go about finding that? Well, we can actually use a simple free body diagram. So what we're going to do is we're going to basically take the tank, and we're going to do a free body diagram of the forces on an element that basically encompasses the entire the entire tank up to bottom, up to depth d. And so the entire element's gonna start at the surface of the water, where we know that the pressure is atmospheric pressure, and it's gonna go all the way in the bottom of it is gonna be at our depth d. And we can actually analyze static equilibrium to find the pressure at depth d. Okay. And so let's look at a free body diagram and apply static equilibrium. Okay, so, and I'm not going to draw it in 3D. So the element would look something like this. And we have gravity going down. Okay, which means inside of the element we have some weight. I'll call that m times g going down, because there is weight of the fluid inside of there, which we need to take into account. And we have a pressure times an area going up, and a pressure times and P naught, which is the atmospheric pressure, times an area, right? So I have this pressure at the surface labeled as P naught. And basically, and remember that the pressure pushes inward on the surface. So the pressure on the top of the water is, or on the top of the fluid in the tank, is pushing down. And the pressure at depth d, because we've drawn our element to be that piece here, is actually pushing up from the bottom. Okay, and I'll just assume that this is of length L here and W here, and the height of it is d. Okay, and so the cross-sectional area here that the pressure is pushing on is just W times d. Or W times L, I should say. Okay, so now, so basically, so the only forces that we need to consider are pressure, the weight. You could consider surface tension, which we did last time, but we're going to in this chapter we're going to completely neglect surface tension. Basically, we're just going to assume that the surface is flat, which means that any curvature of the surface, like any that any meniscus effect, basically causing the liquid to sort of curl up at the side of the tank, is negligible, and which implies there are no shear stresses. So we only have the pressure forces acting on the top, basically pushing down, pressure forces at the depth pushing up, and weight, m times g. Okay, so we apply static equilibrium. Okay, and we're only considering the forces in the y direction, which is why I neglected the pressure pushing on the side. We will deal with that more generally later on. So that implies static equilibrium means that sum of forces in the y direction is equal to 0. That implies that P times A, basically going up, which is minus P naught times A minus the weight, is equal to 0. And recall that this A here is just simply L times W. And the mass, if we assume that density is constant, M equals rho times V. If rho equals constant. Oops, not if rho is equal to constant. Okay, and the volume is equal to L times D times W. So this equals rho W L D. Okay, and these areas are L times W, L times W. Okay, so then we're going to start working with this expression a bit more. So then, P minus P naught, I just combine these two terms here, times the area, which is L times W, equals, just move this term here to the right-hand side, equals rho WLDG. Okay, well, we have a WL over here, so that cancels out with the WL over here. And we can solve for P now. This implies that P equals P naught plus rho G D. Okay, and this rho GD term here is from the weight of the fluid. Okay, in the free body diagram. Okay, and what this expression says is that the pressure in a tank, I'm going to scroll up, that the pressure in a tank, if you know the pressure at the top, the pressure at any depth, if it's in static equilibrium, and if the density is constant, is just a function of the depth. That's it. Okay, and it's simply, the pressure is just the pressure on the top plus rho G times D. That's it. Okay, and this term here, it just represents the weight of the fluid inside of our free body diagram. That's it. So now you may be sort of wondering, what if rho is not constant? What do we do? Which implies that rho equals rho of D. Okay, so what do we do then? And also, this analysis, it only told us about the vertical forces. What about the horizontal forces? So how do we generalize this analysis to account for cases where rho is not constant, or even the gravitational field is not constant? You could have such a thing that, I don't know, if you're working for NASA and you're trying to analyze the pressure distribution in the sun or on Jupiter or something like that. Or if you're an aerospace engineer and you want to understand the forces applied to a tank when an aircraft is doing a very high-speed banking turn, there's going to be an acceleration field that is applied to the fluid in the tank, which is going to cause it to sort of bunch up at one corner here. And that's and while it's banking that corner, it could be in static equilibrium, which means you're going to have different accelerations at different points. So, okay, so now the analysis we did up here was fairly simplistic. We chose a fluid element that had nice flat square sides and it fit the tank. Now, is this very simple result here, is that a consequence of our choice of that very simplistic a free body diagram? Also, we assume that the density here is constant. What if it's not constant? What do we do then? This free body diagram, it had flat sides like that. So is this result here a consequence of that? So I guess what we're asking here is, what happens if we choose an arbitrary fluid element to analyze static equilibrium for? And then how do we generalize it to where the density is a function of depth too, like you have in the atmosphere? Okay, so now we will choose a free body diagram. So the previous analysis, we chose a free body diagram that had flat sides. Are the results dependent on that? So now, what we'll do, rather than analyzing a free body diagram that looked like a nice square and had flat sides, we'll choose an arbitrary element of fluid to analyze. Looks something like that. And we'll have gravity going in some random direction, like that. And this is just an arbitrary free body diagram. Okay, and so we have some net mass times gravity here. So we have a net weight, and on the surface of it, we have pressure pushing against the surface. And again, that's in the opposite direction as n hat. And we have, and on the surface, we have an element of size dA here, and we have a differential pressure force pushing on the surface. Okay. And so now, so we'll have a net pressure force that we can find by just walking around the entire surface and integrating all the pressures on all these little differential patches. And also we'll have a net weight. And I have the net weight drawn here as m times g, but in reality, because the density might be different over here than it is over here, what you have to do is consider the weight in a small little differential volume, like that, and there is, and I'll call that dW, is a force acting on that, and that equals rho at that point times the volume, dV, times the gravity vector. Okay, and so to find the net weight, we basically add up all of these differential weights in all of these tiny little volumes. Okay, and so now we have the mass of the fluid, and the free body diagram is just equal to this. Okay, and I already said this, so I will not say that again. And so then the weight of the fluid in the free body diagram is just m times g. If we assume that g is constant, we can actually yank that out. Again, there are scenarios where some of you might like work for NASA where gravity is not constant. So we have this turns into this expression here, which is equal to the weight. And you can use this expression here to find the net weight if gravity is constant. Basically, you are just adding up all the mass in the entire shape. And here, if gravity is not constant, for instance, there's a stronger gravitational force here than there is over here, or it's pointing in a different direction. Then you need to use that definition there. Okay. So now we find the net weight. Now we need to find the pressure forces. And again, the pressure forces act on the surface in the opposite direction to the surface normal over here. And so again, the pressure force on a small element is just minus P times n hat times the size of this little surface element here. Okay, and to get the total pressure force, you just integrate over the entire surface. So we would have that the pressure force equals the area integral of all the differential pressure forces on the surface, and that equals the area integral of minus P n hat dA, and that equals minus the area integral of P n hat dA. Okay, so now we have the net pressure forces given by this expression here. And I have to note that this symbol here means over an area means it means a surface integral over a closed surface. Okay, which basically means you're taking the entire surface into account. Okay, so we know the pressure forces, we know the net weight, and now static equilibrium still holds, which basically means that the sum of F is equal to 0, and we have everything drawn arbitrarily. So we have the net weight plus the net pressure forces. Well, we use our volume and area integrals that we derived in the general sense. So we have this expression here for the weight, and this expression here for the pressure forces. Well, that implies that basically that implies that the weight of the fluid is equal to the net pressure forces pushing on the fluid element. Okay. Okay, and so in these terms here, we will actually call them body forces in this class, and we'll discuss more about those later. And these are surface forces. Okay, so basically body forces are forces that are occurring from within your fluid element, like weight, and surface forces are forces that are occurring on the surface of the fluid element. Okay, and so unfortunately, this expression here is almost a statement of the obvious, that weight is just equal to pressure. And it's in this abstract volume integral term here is equal to an area integral term here. And it doesn't tell us jack squat about how to find pressure. So this doesn't seem to really tell us anything about how to find pressure. But, so can we do anything to help us out? Because we would like to basically turn this into something that we can actually use. Because if you want to find the pressure force, you need to know the gravitational field and all sorts of geometrical information about that fluid, about that element, about its shape, its volume, etc., 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 which makes it really ugly to use. So, but can we simplify this? Can we do anything with this? And the answer is yes. First, let's recall the gradient theorem, which you guys dealt with in Calc 3. It's really a scalar version of the Gauss divergence theorem. So what that states is that if you have the area integral of some function f, some scalar function f, and hat dA, that is equal to the volume integral of the gradient of f dv. And so let's apply this to pressure. Okay, and so f of p equals the area integral, I should say minus f of p, is equal to the area integral of p n hat dA. Well, we can apply the gradient theorem here to turn this area integral into a volume integral. Well, so that is equal to the volume integral of grad p dv. Okay, so now we can use this result here and substitute it into this pressure force here. Okay, so we basically substitute this into here, and we wind up with substituting we have that the volume integral of rho g dv equals, now the volume integral of grad p dv, well, these are both volume integrals. So we can combine them to have one volume integral of rho g minus grad p dv is equal to 0. Okay, and since our element here is an arbitrary volume. The volume is not zero. Okay, so we are integrating over the total area, and the total volume is finite. So we can't rely on the volume being zero to make this true. The only way to make this expression equal to zero is if the integrand, that is the stuff inside, is equal to zero. So to make this true, for an arbitrary volume, the integrand must be zero. It is the only way to make this true. So basically this term here must be equal to zero. Okay, so this term is equal to zero. So we can conclude that that basically rho g minus grad p is equal to zero to make the integral true. Or rearranging, we have that grad p is equal to rho g. And this is the generalized version of the rule that I showed you earlier. And also recall that if you want to recall that for the Cartesian coordinate system, that the gradient is given by this expression here, where it's just partial p partial x in the I hat direction, partial p partial y in the j hat direction, and partial p partial z in the k hat direction. Now this thing looks a bit more complex than the expression that I derived earlier, but is it consistent? So basically, is this consistent with the earlier result? And in the earlier result, we had and to do that, we can actually work with this expression here, and we can do a line integral. Okay. Okay, and basically what we can do is we can actually use this expression directly, and to find our pressure at depth d, we can actually do a line integral from the surface and going down. So we can do a line integral. Now, don't be scared when I mention the line integral. For this case, because we are assuming in this class that g is constant, the line integrals actually become very simple. And so, but just recall the fundamental theorem of line integrals. Okay, and the fundamental theorem of line integrals states that for some scalar gradient, grad phi, equals some vector function f of x, that phi2 minus phi1 equals the integral of the starting point of a path to the end of the path times f of the position vector times ds along the path. Okay, and so basically what that means is that, and you guys probably seen this in your Calc 3, where we have some sort of scalar field for phi, and we are starting here, and we are ending here, and basically for this conservative vector field, and if there's a gradient there, it is conservative, and that gradient satisfies certain properties, and definitely a constant vector field satisfies those certain properties to make this true. Basically, we can, if we want to find the difference of phi, we can just basically integrate f along any path, and we can find phi2 minus phi1 just using this, just using that definition. And recall that from your calculus that it is path independent if the vector field here is conservative, and our vector field is certainly conservative. Okay. So we have the setup here that we have for line integral is exactly what we have for pressure. Okay, so we have the same setup, except for the scalar field is pressure, and our vector function is just rho times g. Okay, so let's apply the line integral. Okay, and so again, as I said before, we have our tank here, we have the surface here, and we want to find the pressure at depth d. Well, we're going to start from a point where we know the pressure, that's the surface, and again, that's given by the triangle with the three little lines underneath it. And we're going to start at point 0, I'll call it, and we're going to go down to point D. And so we're going to do a line integral to find the pressure at depth D. Okay, so let's apply the line integral. And so we have P of D, which is the end of our path, minus the pressure at the start of our path, which is P naught, equals the integral from the beginning of our path, S naught, to the end of our path, S, I'll call that as some path length at D, times our vector function, which is rho g, dot with ds. Okay? And I'll move this over a little bit more. Okay, and so basically S naught here is 0, and SD here is just D, because again we're just integrating over our path, which is straight down. Okay, over the length of the path. Okay, so well, G is just rho g j hat. Remember, I have y pointing down here, and for ds, we can choose a path. Let's choose the simplest path and choose one that is going straight down, like I alluded to earlier. But it does not matter what path. We could go like a drunken walk. We could go like this and wind up like that. But it might be hell to integrate that path. So instead, just choose a nice, easy, straightforward path. Okay, and that implies that ds is just dyj hat. Okay, because we're going to start from the top and then go straight down. Okay, then the pressure at depth d equals P naught equals the integral along the path from the starting point, which is 0, to the depth d, because again, we just need the entire length of the path, times rho g j hat dot with dy j hat. Well, j hat dot j hat is equal to 1. So that equals the integral from 0 to d of rho g dy. Okay, and so this 0 point here is the surface, and this point here is at depth d. Okay, then what this gives us here is that if g is constant, we can pull that out. Okay, so what we have here is that, or simplifying, we have P of D minus P naught equals gravity, if it's constant, times the integral from 0 to d of rho dy, or if rho equals a constant, we have that P of D minus P naught equals rho g d. Okay, and this result is consistent with the earlier result. In fact, it's the same. Okay, so that means that truly for an arbitrary shaped fluid element, that our result that the pressure is a function only of depth is consistent with is consistent between the two different analysis techniques. Except for this one is a bit more general because it tells us what to do if the density is not constant. Basically, if gravity is constant and density is not constant, then we need to do the integral of rho over the entire height here to account for the variable density. And if you're working for an astronomer or something like that, where both rho and g may be both non-constant, then you got to do this integral over here of rho times g. Okay, so the result of the more complex analysis, but in my opinion much more elegant, turned out to give you the exact same result. And the line integral, which initially looks scary, but because gravity points down and it's constant, it actually turns out to be pretty fairly straightforward. And so now we looked at the pressure variation with depth. Now we can use the line integral in this generalized expression to understand, to ask the question, so we've only considered the vertical direction. Does pressure vary in the horizontal direction? So that is, does P vary in the horizontal direction at a constant depth? So let's just consider a little complex tank here. So we have a tank here, and so we have a sort of little surface here that is submerged, and it's supposed to be at a constant depth. I'm not very good at drawing. So is the pressure at any point in the surface, is it a function of where you are at a given depth d? So basically we've determined the pressure as a function of y, but is the pressure also a function of x and z? Is it a function of those? Okay. So how does the pressure vary at constant depth? Well, let's look at let's do a line integral between point 2 here and point 1. So we have P2 minus P1 equals the integral over S1 to S2. It's just along the entire path of rho g dot ds. Okay, where again g equals g j hat, and ds, now we're going in the horizontal direction, so ds will equal to some dx in the I hat direction. I didn't specify whether we're going in x or y, plus a dz in the k hat direction. Okay, and so this will then equal the integral from our starting point to our ending point of rho g j hat dotted with ds, which is dx I hat, plus dz k hat, which is equal to 0. And the reason that's equal to 0 is because I hat dot j hat is equal to 0, and and k hat dot j hat are equal to 0. So basically the integrand is 0, which implies that P2 minus P1 equals to 0. And this implies, and this result implies that implies that pressure does not vary in the horizontal direction. That is, the pressure is the same here as it is over here, as it is over here. But now if I chose a different plane, like maybe one that's up here, then the pressure between this point and that point would be different, but the pressure between that point and this point, when they're on the same plane, would be the same. and so what this means is that the pressure for a static fluid is a function only of the depth. Okay, and the other way that you can sort of show this is you can work with our result directly. So alternatively, we have G equals GJ hat, and recall that grad P equals partial P partial X I hat plus partial P partial Y J hat plus partial P partial Z K hat. And we also had that grad P equals rho G. So we can take this for G and substitute it into here. Oops, I forgot the vector arrow. And we can take grad P and substitute that in. So this implies that, I'm just going to be lazy and copy it, that partial P partial X I hat plus partial P partial Y J hat plus partial P partial Z K hat is equal to G J hat, or equal to rho G J hat. Okay, so we gather components. So in the I hat direction, we are left with partial P partial X is equal to 0. Okay, which basically means that there is no pressure gradient in the X direction, which makes sense. So this implies that P is not equal to a function of X. Okay. So again, because we have a partial derivative here, if a partial derivative is not equal to 0, it does not mean that pressure is constant. It means that pressure is not a function of this X derivative here. And we can do the same thing for K hat. We have partial P partial Z is equal to 0, and that implies that pressure is also not equal to a function of Z. Okay. So we can put these two together, and that pressure is only equal to, well, which is in general equal to a function of X, Y, Z, and time. We are neglecting time here. We've already shown that it's not a function of X, and we've shown that it's not a function of a Z. So this means that P equals P of Y for fluid statics. Okay, and because we're assuming static equilibrium, the time variation of pressure is implicitly assumed to be 0. So now let's work with the last direction. We have partial P partial Y is equal to rho G. Okay, but P equals only a function of Y. We just argued that, which implies that partial P partial Y equals dP dy, or dP dy equals rho G, and we can integrate this. This is really a differential equation that we have to solve, but this implies that pressure at depth D minus P naught equals the integral from 0 to D of rho G dy. Okay, and that's the same as above. Okay, in this case, either or worked. It's a really bad Y. Let me fix that. dy. And that's the same result as above. And also the same result as above is that the pressure is not a function of X or Z, which are the two horizontal directions. So also we conclude that pressure is a function only of the depth, and that's it. Okay, and that I will stop.